adopt what is called as the mixture fraction formulation in trying to describe diffusion flames. This is actually a powerful idea for combustion in general and with particular context of diffusion flames and partially premixed flames. So the idea basically is we now try to define this variable called the mixture fraction. Mixture fraction, extremely useful in diffusion flames and partially premixed flames. So what we will do is let's consider a two-feed system. That means we have two inlets that are allowing gases to come. So we are looking at a homogeneous gaseous system, and let us say that 1 represents fuel stream and 2 represents oxidizer stream. In fact, we will try to adopt this for a general hydrocarbon fuel, hydrocarbon oxidation. That means when we now say oxidizer, we will mainly be thinking about O2, and for the fuel we might mainly be thinking about a CmHn kind of hydrocarbon, right. So then the way the mixture fraction is defined is essentially like a mass fraction, okay. So the mixture fraction represents the mass fraction of the fuel in the mixture, right. That means let's say Z is the symbol given to mixture fraction, then this is basically m dot 1 divided by m dot 1 plus m dot 2, where m dot 1 is the mass flux of or the mass flow rate of the fuel stream, m dot 1 is m dot 2 is the mass flow rate of the oxidizer stream. And of course what this means is the mass fraction of the oxidizer then is oxidizer in the mixture is then 1 minus Z, alright. It would be defined as m2 dot divided by m1 dot plus m2 dot, therefore it's 1 minus Z. Now each stream contains diluents. It's not as if like the fuel stream is fully fuel. You could have some nitrogen, you could also have the oxidizer stream is like a, let's say, air, and most of it is nitrogen, so you have only part of it is oxygen. So contains diluents different extents, right. Then what you are looking at is the mass fraction of the unburned fuel in the mixture. What we expect is it should be proportional to the inlet mass fraction of the fuel in the fuel stream times the mixture fraction. So the mixture fraction is a fraction of fuel when compared to the total. So the mass fraction of the unburned fuel in the mixture is proportional to the inlet fuel mass fraction. So that is to say YF comma U, that is the unburned fuel mass fraction anywhere in the mixture, can then be written as Z times YF comma 1. So YF comma 1 is essentially the mass fraction, fuel mass fraction at at the inlet to stream 1, right. Now previously we were using the symbol YF naught for this purpose. The corresponding oxidizer would be YO naught. Well, this allows for us to actually think about a YF2, which means you could also dope some fuel into the oxidizer stream and vice versa. Alright, so this notation somewhat is a little bit more general. Of course it's not too general, it is still confining ourselves to two streams, alright, but we could say YF1, YF2, YF3 and so on. Okay, so this is a little bit more general notation then. And similarly the unburned oxidizer mass fraction is YO2U is equal to 1 minus Z times YO2 comma 2, right. So YO2 comma 2 is actually the oxidizer mass fraction at inlet to stream 2. So for example, if it were air, this number would be like 0.23 or so, right. With this, if you now think about it, what happens is your unburnt fuel mass fraction or the unburnt oxidizer mass fraction both vary with the mixture fraction Z linearly. Okay, in other words, if Z were more, your YFU would be more at a place proportional to YF1, right. If Z were more, YO2 unburnt will be less correspondingly proportional to YO2 So if this is represented in a graph that could go like this, so if you now plot Z along the horizontal axis, it goes from 0 to 1. So if your mixture fraction is going all the way from 0 to 1, 0 would correspond to no fuel and 1 would correspond to all fuel, alright, no oxidizer. And therefore as Z keeps on increasing, then you have a straight line that keeps on increasing from 0 all the way to YF1. This is to say, in the mixing field at the inlet you would have only oxidizer in the oxidizer stream, and you will have no fuel at all in the you would have YF1 in the fuel stream, and you would have no fuel in the oxidizer stream, and anywhere else in the mixing field you would now have a mixture fraction which is having different values, and corresponding to that the fuel mass fraction would lie on this line. essentially, alright. Similarly, if you want to think about how the, so this is the plot of yf comma u. Similarly, if you want to look at the plot of yo2 comma u, that's another straight line that starts with the value of yo2 comma u, let's say at the oxidizer stream inlet where you don't have any fuel, and goes all the way to 0 at the fuel inlet where you don't have any oxidizer. Anywhere in the mixing field your mass fraction of the oxidizer lies on this line corresponding to whatever is the mixture fraction locally, right. So this is regarding how the unburned fuel and unburned oxidizer mass fractions work out. What we want to now do is to further proceed and see if we can actually get mass fractions of burnt products, right, and where you have where you are in non-stoichiometric proportions, you will have excess fuel and excess oxidizer depending upon which is in excess, whether you are in fuel rich or fuel lean conditions, and we would like to also find out what is the burnt fuel concentration and the burnt oxidizer concentration depending upon whether it is excess or not. So for which we now have to actually go through what happens when you have a reaction. So in a reaction we had, this is long ago, we came up with this dy1 divided by w1 times nu1 double prime minus nu1 single prime, etc. You could also write, of course, one more, dy2 divided by w2 times nu2 double prime minus nu2 single prime, etc. And the general ith species, you could say dyi divided by wi times nu I double prime minus nu I single prime. I'm sure you recall this. So let's suppose that you can call this set of equations a star. We will pick at least two of these in order to integrate it at different times in the near future. So for a single component general hydrocarbon, that is to say you don't have different mixtures of hydrocarbons. For example, if you take liquid petroleum gas, it's actually a mixture of hydrocarbons, butane and propane. So instead of that, if let us suppose that we are considering only one hydrocarbon at a time, hydrocarbon fuel, and let's suppose that we write this equation as nu f single prime Cm Hn for the generalized hydrocarbon that we considered, plus nu O2 single prime O2 gives nu CO2 double prime CO2 plus nu H2O double prime H2O, right, with nu F single prime equal to 1 fixed arbitrarily. Let's suppose that we just say we are interested in 1 mole of this hydrocarbon, right. We could get nu O2 single prime equal to m plus n divided by 4, nu CO2 double prime equal to m, and nu H2O double prime equal to n over 2 as stoichiometric coefficients. That means these values correspond to the reaction happening stoichiometrically, right. That means you don't have any any of the fuel or oxidizer left over as part of the products, right. Now at the stoichiometric surface in the mixing field, we then have the number of moles of oxygen unburnt divided by the number of moles of fuel unburnt at stoichiometry equal to mu O2 single prime divided by nu F single prime, right, as given above. So in terms of mass fractions, so this is mole fractions, so in terms of mass fractions, well the above is in terms of moles, not moles fractions, I'm sorry, but of course you can divide by the total number of moles and get the mole fractions as well. So here we are going to be looking at the mass fractions Y O2 unburned divided by Y F unburned at stoichiometry is nu O2 single prime molecular weight times molecular weight of oxygen divided by nu fuel single prime times WF, which let's say we call as nu, which is the stoichiometric mass ratio. So what we want to do is we want to see if we can integrate this equation for a situation where you have a stoichiometric reaction, so that we can make use of the fact that you're not going to have any of the reactants left over, all right. So for a stoichiometric reaction, both fuel and oxidizer are completely consumed, right. Therefore we use this to integrate the this equation here star at any mixture condition relative to the unburnt mixture, because you're not going to have any of the reactants left over. So you can now say we integrate star at any mixture condition. That means you can look at any intermediate mixture condition relative to the unburned condition, right. That means the limits of integration go from unburnt values to any value during the reaction as YO2 minus YO2 comma U divided by nu O2 prime WO2, right. You can just pick, let's say, oxidizer and fuel, then you would get YF divided by minus YFU divided by nu F single prime WF, or rearranging this, all this means is nu yf minus yo2 equals nu yfu minus yo2u, right. So what this tells us is this is sort of a preserved quantity, right. You started out with unburnt values yfu and yo2u at a point in the mixing field in a proportion with a nu here, right, where should I have yes, nu, that's right, you got this nu. So and that is the same even during the reaction between the two. That's essentially the idea. Okay, so whatever is the unburned values, that difference is what is preserved. So what you can then do is we are interested in writing everything in terms of the mixture fraction. So we had the yfu in terms of mixture fraction and the inlet mass fraction. So here yo2u in terms of mixture fraction and the inlet mass fraction of the oxidizer. So substituting the expressions for yfu and yo2u in terms of Z. In here we get and then of course rearrange. So you say Z equals nu times yf minus yo2 plus yo2 comma 2 divided by nu yf comma 1 plus yo2 comma 2. So you can see that yo2 comma 2 yf comma 1, these things are showing up from the inlet mass concentrations, mass fractions of the oxidizer and fuel in the respective streams. So for stoichiometric mixture, nu yf should be equal to yo2. In fact, this is what we had also got for the Berg-Schumann solution, where we said gamma is equal to 0 means beta is equal to 0, that means alpha f minus alpha o is equal to 0, right, and that amounted to exactly this. We say yf divided by yo2 is or rather yo2 divided by yf should be equal to nu, and that should be the same as yo2u divided by yfu, right. The unburnt mass fractions should be in stoichiometric proportions just as well as whatever is in the reaction. Okay. So from this what we can do is this will actually now tell us what should be the stoichiometric mass fraction, right. So the stoichiometric mass fraction is ZST equal to 1 plus nu yf comma 1 divided by yo2 comma 2 the whole to the minus 1. I should be able to show that, right. If you now say this is going to go away, right, then you rearrange. What this tells us is there is a particular value of Z which is the stoichiometric mixture fraction naturally, and it is related to how the inlet stream mass fractions of fuel and oxidizer work out, right. So if Z is less than ZST, right, we are less in fuel, so as Z keeps on increasing you have more and more fuel, that's essentially the idea. So if Z is less than ZST, we know clearly that it is fuel deficient, right. Deficient or fuel lean, whichever way you want to, right. Then YF burnt is going to be 0. This is now the mass fraction of fuel in the burnt products. So you're not going to have any excess fuel in the products. Therefore, you can now substitute YFB equal to 0, which terminates the combustion, right. So the combustion essentially doesn't proceed simply because you run out of fuel. You don't have any more fuel. So plug this in Z expression, right, and use definition of ZST. You should now get, so if you now plug in the expression for Z, YFB is equal to 0, then from there you now rewrite, you should get YO2 comma B equal to YO2 comma 2 times 1 minus Z divided by ZST for Z less than or equal to ZST. Similarly, for fuel rich mixture, right, combustion terminates when YO2B equal to 0. So you now plug this in the expression for Z and rewrite for YFB. You now get an expression YF comma B equal to YF comma 1 times Z minus ZST divided by 1 minus ZST. And this is valid for Z greater than or equal to ZST. That means we can now draw a picture similar to this. This is for the unburned fuel and unburned oxidizer in the mixing field, but we can now anticipate how the burnt fuel and burnt oxidizer should look like. If you now have Z going in the horizontal axis from 0 to 1, somewhere in there you should now be able to locate Z equal to ZST. Now that becomes an important thing, whether are we on this side of ZST or that side of ZST, because this is going to correspond to a fuel lean situation, that's going to correspond to an oxidizer lean situation. Therefore, we should now get your YFB is valid only for Z greater than ZST, right. On this side your YFB is equal to 0. Therefore, you have, and this is also linear in Z, okay. So this goes, so your YF comma B is going to go all the way to from 0 to yf comma 1, right. As a matter of fact, when you go to this corner, when z is equal to 1, your yf is equal to yf1, you know, and so sorry, z goes to 1, so yfb goes to yf1, all right. And this is what we were looking at the last class, where at the flame you now have the fuel concentration go all the way to 0 and then stay flat on the other side. Okay. So here the fuel is going to go all the way from the fuel inlet stream all the way down to 0 at the stoichiometric surface and then lie flat on the oxidizer rich side, right. And similarly you now have a straight line that goes from 0 here backwards to YO22 in the mixing field. So essentially, if it's possible for us to now go back and redo the Birch-Schumann problem in terms of Z instead of beta, which is not very different if you think about it, all right, and that's also possible, then you can actually look at contours of Z, several contours of Z, and depending upon the contours of values of Z, you now try to actually look at what the values of YFB and YO2B should be. You now can map how the fuel concentration and oxidizer concentration should show up. This is still for the excess fuel this side for the products and excess oxidizer in the products for fuel rich side and fuel lean side. Still haven't talked about the actual products of combustion, right, like CO2 and H2O. So for getting the product concentrations, we should do something similar to what we have done here. In order to obtain your new CO2 double prime and new H2O double prime, all we have done by saying we are balancing this reaction is to basically conserve atoms. We compared carbon atoms, hydrogen atoms, oxygen atoms, and then came up with these things. So we conserve atoms across the chemical reaction to obtain product mass fractions as a function of Z. So still we are interested in what happens as a function of the mixture fraction Z, and that's a hero for the day, mixture fraction. So we keep on looking at everything as a function of Z. So element mass fractions, so you look at what happens in the unburned mixture, element mass fraction in the unburned mixture so look at the fraction of carbon atoms. So you had m carbon atoms in the hydrocarbon, right. So this is m times molecular weight of carbon atom divided by the molecular weight of the fuel, right, times yf comma u. So this is the mass fraction of the unburned fuel times this fraction is what's going to give you the carbon fraction. Similarly, if you now look at ZH, that's going to be N times WH divided by W fuel times YFU. For the oxygen, it's mainly coming from the oxidizer stream, so we might as well just write ZO equal to YO2U. Whatever is the mass fraction of the oxygen in the oxidizer stream unburnt, right, is the ZO. Of course, from here we should now be able to also write CC that YFU is equal to WF times N ZC divided by WC plus M, did I make a mistake? ZH by WH. All right. On the burnt side, on the burnt side for the products, the element mass fraction or for the carbon we have ZC equal to MWC divided by WF YF comma B. That's actually for if you have excess burnt fuel, right, plus if carbon is also there in carbon dioxide, that's what we are more interested in, WCO2 times CO2 burnt, and this is what we are trying to find out in terms of Z, okay. And hydrogen is going to be like N times WH divided by WF YF comma B plus twice, because water contains 2 hydrogen atoms, so WH divided by WH2O times YH2O comma B. This is also the next thing that we are trying to find out in terms of Z currently. So, and finally we have to conserve oxygen atoms, so ZO from the products would be twice WO divided by WO2 YO2 comma B plus twice WO divided by WCO2, because there are two oxygen atoms in carbon dioxide, YCO2 comma B plus 1 WO divided by WH2O YH2O comma B, right. So now if you now equate these, so use YFU and YO2U in terms of Z in ZC, ZH, ZO, and rewrite, okay. So you then get YCO2B would be YCO2 stoichiometric times Z divided by ZST, and YH2O comma B equal to YH2O stoichiometric times Z divided by Z stoichiometric. This is for Z less than or equal to ZST, or YCO2 comma B equal to YCO2 stoichiometric times 1 minus Z divided by 1 minus Z stoichiometric, and YH2O comma B equal to YH2O stoichiometric times 1 minus Z divided by 1 minus ZST. This is for Z greater than or equal to ZST, where we have to say what is YCO2 stoichiometric and YH2O stoichiometric. So YCO2 stoichiometric is YF comma 1 ZST times M WCO2 divided by WF and YH2O comma stoichiometric is YF comma 1 ZST N WH2O divided by WF. All right. So what do you expect? We can still see that YCO2 is still going linearly as Z, YH2O is going linearly as Z, so long as Z is less than ZST. YCO2 is still going linearly but decreasing with Z, YH2O is decreasing linearly with Z as Z is greater than, right. So let's think about plotting this. So you still have Z along the horizontal axis going from 0 to 1, and we now locate the stoichiometric surface at somewhere in between, and we noticed earlier from that picture, just to reproduce, your YF comma B goes from 0 at the Z equal to Z stoichiometric to YF comma 1 when Z is equal to 1. This is the excess burnt fuel, and you now have YO2 comma B going all the way up to YO2 comma 2 at Z equal to 0. But what we are looking for now is how this varies. YCO2 goes to a peak value at Z equal to ZST and then comes all the way down to 0. So this is your YCO2 comma B, and similarly, of course, depending upon the numbers, you should now get a similar set of lines for YH2O comma B. So it reaches a peak value, you get the same expression, same numbers I should say, from both the expressions at Z equal to ZST. You can plug that and then see what happens, right. Now we are still interested in the temperature. So for temperature, all these things are essentially like looking at an equilibrium, you see. So for the temperature, we now say for an adiabatic flame, right, for an adiabatic flame we have the unburnt enthalpy equal to the burnt enthalpy, and it's probably a good time to stop. I'll just stop here.